Have you ever seen something levitate and thought, whoa, that's gotta be magic? Well, what if I told you that magic is the key to understanding one of the most powerful forces in our world? Today we're going to start by making a metal ring float in midair. And believe it or not, by the time they're done, you'll see how that exact same principle is what powers, well, pretty much everything. Let's dive in.
So this is the big question for today. Seriously, think about it. Every single time you flip a light switch, you're tapping into a massive network of power. But where does it all start? How do power stations actually make that electricity from things like wind or water? The answer, it turns out, is this incredible dance between magnetism and electricity. And we are going to break down every single step. All right, here's our roadmap. First, we'll tackle that magnetic levitation mystery. Then we'll use what we learned to understand the AC generator. After that, we'll see how to create direct current, or DC, compare the two types of generators, and finally, bring it all home, literally, to see how this powers your house. Okay, part one. So how in the world do you make a metal ring just float? I know, it looks like a magic trick, but it is pure, awesome physics. And get this, the rule that makes this ring float, it's the exact same rule that generates pretty much all the electricity on the entire planet. So yeah, understanding this first step is absolutely crucial for everything else we're going to talk about. The setup here is actually pretty straightforward. You've got an iron core, you wrap it in a copper coil, boom, you've got an electromagnet. Now, we just place a simple metal ring over it and we hook the coil up to an AC power source. That's alternating current. Now watch what happens when we flip the switch. Just like that, the ring levitates. So what on earth is going on? Okay, but here's where it gets really, really interesting. What if we swap out that AC power for a DC source? Direct current, like from a battery. Let's see what happens. Whoa, it jumps. It jumps for a split second, and then it just falls right back down. No floating. So that's the mystery, right? Why does it levitate with AC, but only give us that little jump with DC? The whole secret is right there in the name, alternating current. AC power isn't a steady stream. It's constantly changing, flipping its direction back and forth super fast. And because the current is always changing, the magnetic field it creates is also always changing. It's getting stronger, weaker, flipping its north and south poles. It's this non-stop change that creates a current in the ring. Now, DC, well, DC is just a steady one-way street. The power flows, the magnetic field turns on, and then that's it. It just stays on. The only change is that one little moment you turn it on, and that's why we only get that one little jump. So why does this happen? It all boils down to a fundamental law of physics called Lenz's law. And the easiest way to think about Lenz's law is that nature is, well, it's kind of stubborn. It doesn't like change. So when the coil's magnetic field is constantly changing, it forces a current to flow in the ring. And that new current in the ring creates its own magnetic field with one single purpose: to fight back and oppose the change. It's like a constant magnetic arm wrestle. The coil's field is always changing, and the ring's field is always pushing back against it. And it's that constant repulsive force that's strong enough to fight gravity and make the ring float. Okay, so let's recap. We've just seen that a changing magnetic field can create a current in a wire that's just sitting there. Now, let's flip this whole idea on its head. What if the magnetic field is stationary, and instead we move the wire through it? Well, you probably guessed it. It does the exact same thing. It creates a current. And folks, that right there, that is the core principle behind every single electric generator on Earth. So let's look at the basic parts of an AC generator. First, you need a strong permanent magnet. That's what creates our magnetic field. Then, you need a coil of wire. We usually call this the armature, and this is the part that's going to spin. And finally, you need a way to get the electricity out of the spinning coil. That's where these things called slip rings and carbon brushes come in. They're basically clever contacts that let us tap into the power without everything getting tangled up. All right, here is the absolute core principle. We use some form of mechanical energy, say from a spinning turbine, to physically rotate that coil inside the magnetic field. As it turns, the amount of magnetic field that's actually passing through the coil is constantly changing. We have a fancy name for this, magnetic flux. And here's the magic. Thanks to Faraday's law, whenever that magnetic flux changes, a current is created. That's it. We are literally turning physical motion into electricity. Okay, a quick question for you. As that coil is spinning around and around, do you think the current it produces is just a steady, constant flow? Nope, not at all. The current actually goes up and down, from maximum all the way to zero, and it all depends on the coil's position. So let's think about that for a second. When is the current at its peak, and when does it drop to nothing? Let's break it down. Picture the coil lying flat, or horizontal. In that position, its sides are moving up and down, cutting through the magnetic field lines at the fastest possible speed. It's like slicing through them at a perfect 90-degree angle. That's when you get the maximum current. But now imagine the coil is standing straight up, or vertical. For just that one instant, the sides of the coil are moving parallel to the field lines. They're not cutting them at all, they're just sliding alongside them. And if you're not cutting the lines, you get zero current. It's that simple. But wait, there's another twist. Think about one full rotation. On the first half of the spin, one side of the coil is moving up. On the second half, that same side is now moving down. Because the direction of motion has flipped relative to the field, the direction of the current also flips. This happens every single half rotation. And this constant back and forth reversing flow of electricity, well, that's what we call alternating current, or AC. It's the natural default output of a spinning generator. So AC is what we laterally get. But think about all the electronics you use, especially anything with a battery. They don't want a current that's flipping back and forth. They need a nice, steady, one-way street of electricity. They need direct current, or DC. So how do we fix this? How do we take that alternating output and make it flow in just one direction? Well, the solution is an absolutely brilliant, yet surprisingly simple piece of engineering. And you'd be surprised at how small the change is. To turn an AC generator into a DC generator, you only have to swap out one part. We take out those two separate slip rings we had before, and we replace them with this, a single ring that's been split right down the middle. This amazing little invention is called a split ring commutator, and this is the entire secret to making DC power. Okay, now here's the genius of it. The commutator spins right along with the coil, and it's designed so that at the exact moment the current inside the coil is about to reverse direction, the two halves of the split ring swap contact with the brushes. So think about it. The current inside flips, but at the same time, the connection to the outside circuit also flips. One reversal cancels out the other. It's like a perfect little switcheroo every half turn. And the result? The current going out to your device always flows in the same direction. All right, so let's put these two head to head. Seeing the AC and DC generators side by side really makes the key differences pop. So the number one difference, the one you absolutely have to remember, is the key component. An AC generator uses two slip rings. A DC generator uses one split ring commutator. That's it. That one mechanical difference is what changes the output. With AC, you get that classic sine wave that goes both positive and negative. But with DC, thanks to the commutator, you get this pulsating output that always stays on the positive side. It still goes up and down, but it never, ever reverses direction. Now, if you're ever asked in an exam for the principle of an electric generator, this right here is your perfect 3-mark answer. It's all about electromagnetic induction. You rotate a coil in a magnetic field. That changes the magnetic flux linked with the coil, and that change in flux is what induces the current. That's the whole story in one perfect sentence. Okay, we've gone deep into the physics. Now it's time to zoom all the way out and connect this back to that very first question we asked. How do giant power stations actually get electricity to your home? When you get right down to it, every power plant on Earth is basically a giant energy conversion machine. Their entire job is to turn mechanical energy into electrical energy. And the way they do that is by getting something to spin really, really fast. That spinning thing is called a turbine, and it's hooked up to a massive generator. A generator that works on the exact same principles we've been talking about. It takes that spinning motion and turns it into a massive flow of electricity. And really, it doesn't matter what you use to do the spinning. Whether it's steam from burning coal, water rushing through a dam, or wind pushing a giant blade, all of those things are just different ways to turn a turbine. The turbine spins the generator makes AC electricity, and that electricity gets sent out to our homes. And hey, remember that levitating ring from the very beginning? That same idea is probably in your kitchen right now. An induction stove works by creating a changing magnetic field that induces a current directly in your metal pot or pan, heating it up instantly. It's the same physics. So let's just bring this all home to one final powerful takeaway. From that little floating ring to the massive power stations that light up our world, it's all based on the exact same rule. If you remember nothing else, remember this. Whenever a conductor cuts magnetic field lines, electricity is generated. That's it. That simple interaction is the engine that runs our entire modern world.